2 threads, 1 shared counter, and your final value is wrong. That's a race condition. The most direct fix is a mutex, a mutual exclusion lock. Python's threading module gives you threading.lock. Acquire it before accessing shared data, do your work, then release, ensuring only one thread runs that block at a time. The with statement handles release automatically, even on exceptions. When using multiple locks, always acquire them in consistent order to prevent deadlock. For simpler needs, Python provides thread-safe structures out of the box. Q.Q handles producer-consumer patterns with built-in locking. Collections.deque supports atomic appends and pops. And while the CPython GIL makes simple assignments atomic, never rely on it for multi-step logic. The cleanest approach is to eliminate shared mutable state. Use immutable objects, named tuples or frozen data classes, so threads can read freely. For per-thread state, threading.local gives each thread its own isolated copy. Or adopt message passing. Threads share data through queues, never touching shared memory directly. For complex coordination, Python offers higher-level primitives. A semaphore limits concurrent access, great for connection pools. A condition variable lets threads wait on a specific state change. And concurrent.futures provides clean thread and process pool APIs, abstracting away raw synchronization entirely. Race conditions attained with locks, thread-safe structures, immutability, and higher-level abstractions. Master these, and concurrent Python becomes predictable. Want to nail questions like this in your next interview? Interview Mentor gives you hands-on practice with real questions. Every answer gets a grade with specific, personalized feedback. Track your progress across topics and difficulty levels.